Hello. In this video, I'm going to be going over axial loading, a statically determinate problem. Okay, so this is the first problem I'm going to be going over. It's also the most basic, just kind of going over, the most basic concepts and working through it. So here's the problem we have. A circular shaft, 50 inches long, that has a completely uniform diameter and is all steel. So that means for all segments, it's going to have the same Young's modulus, 30,000 ksi, and the same area, 0.9 inches squared. Now, in this problem, you are given the area first, and you also know it's a circular shaft. It's a cylindrical shaft, rather, and then you can just back solve from that to get your diameter, which comes out to 1.07 inches. You need to know both the area and the diameter to enter in the program. Okay, so looking at loads on the shaft, on the far right you have an 80 kip load, and halfway across there are two 10 kip loads. Now remember, one thing that you can do with these two 10 kip loads is that you can reduce them to a single equivalent load on the central axis, which would be 20 kip. This is because both of them are completely perpendicular to the central axis, so you don't have to worry about any angles or components. We're just looking for loads directly. I guess if you said up and down was the y-axis, and then there's the x-axis, there's no y forces entirely. So 20 kip equivalent load on the central axis at the center. Now in terms of compression and tension, you can see the left end is clamped here, so the 80 kip force is pulling away from the clamp, it's pulling the shaft in tension. The 20 kip equivalent is moving towards the clamp, it's pushing the shaft in compression. And remember, tension is considered positive, compression negative. So we can bring up our program and start entering this in. Now, first thing that'll pop up here is a box about how to break it up into segments. And it goes through here: uniform diameter, uniform geometry, composition, shear modulus. Basically, segments are going to have uniform everything, and as soon as there's a change, it begins a new segment. So looking at this, how many segments do we have? Well, starting from the right, you have this 80 kip, then it's completely uniform until you hit the 20 kip equivalent, which is a change, so you begin a new section. And past that, there isn't really any change until the end of the shaft, so you only have two segments. And note that even though uniform diameter, material, everything, you're just looking for any change. So just that 10 kip or 20 kip is the change that breaks it into a new segment. So we can enter in our information for segment 1. Because both of these segments, they're going to have the same uniform geometry and everything, it's only the load that changes. So at least for this segment data, for both sections, it's going to be exactly the same. They both have 1.07 diameter inches, 30,000 ksi. Remember to enter it as psi because that's your base unit. And there's no inner diameter or anything. It's completely solid shaft. So those will just come up as not applicable. And the area as given 0.9 inches squared. Okay, now in the segment 2, remember everything works from left to right, as it says here, shaded yellow. And segment 2 has the same information. Okay, so now we get to add forces. There's only two forces on this, two loads on this shaft. You have the 80 kip on the right, and remember we made the 20 kip equivalent, leaving just two total loads. So 2. Working from the left, the first one that you reach is that 20 kip. So 25 inches, negative 20,000 pounds, which is, 20 kip. Negative because it's compression. All the way across is the 80 kip. And this problem only has a left clamp. If it had the left and right clamp, it would be an indeterminate problem, which I will go over in later videos. This here goes over the difference between segments and sections, where sections has uniform force, has all the same uniforms that a segment will have, but also having uniform force. And this problem has two segments and two sections. It's because both of them line up perfectly. And we had it draw at the bottom. You can see it draws it out, and it has the same layout as what I have already made. So we can go on and solve. Okay, so in this little table, we start putting in values for all of our calculations. So starting from the right and working left, we start with segment 2, doing your summation of forces. You can see that the reaction load within the material, P2, only has the other 80 kip on the end, so equal. Now, force inner, stress inner, remember we just have a solid shaft, so we don't have to consider any inner anything. They're automatically filled out for you. Stress, P over A, comes out to this, 88,000. 88, so 0.89. The elongation, PL over AE, 0.07407. Let's do something here quick. What if I just enter it as 0.074? Now, when you enter in, or don't enter in anything, or enter in something wrong, it'll come up as a question mark, and it has this value check that popped up. And it kind of runs you over some things to double check. Double check that you're using the right values for your segment, that you're summing up the force correctly, and that you are using that section's length in your calculations. But why was that wrong? Entering 0.0. This program operates under a certain level, a certain amount of significant digits required for it to accept answers. So 0.074 is not accepted. However, 0.0741 is accepted. That's because it wants 4 significant digits. So now we can move on to section 1. Section 1 is you leave on section 2, or at least the loads applied from section 2, and then now you add on section 1. This brings into play that 20 kip equivalent, affecting your summation of forces. And once you have that reaction, this should actually say P1, then you can solve for your stress and the elongation. So we can put that in 60 kip outer stress and the section's elongation. Now I have these written out to 5 significant digits. Simplifying it down to 4 is perfectly fine. It will accept either, as long as you have 4 or more. And that's it. Solution complete. Remember, for the total elongation, all you have to do is just sum up the elongations of section 1 and section 2. One thing to remember that might be kind of confusing is that when you're looking at this section, right now we're looking at section 1, even though I have section 2 on here, it's only on there to include the loads on it. When you're going for your elongation, only use the length of the section you're analyzing. So we only use section L1, the length of section 1. Do not add on the length of section 1 onto section 2. Otherwise, you'll get the wrong values. And you can see here, it's just 25 inches. So that should be it for this problem. It's fairly simple. Would only take just a couple minutes, just adding in information and all of that. The next problem, I'm going to go over what to do when you encounter having a hollow section in the shaft.